We throw the words mass and weight around like they're the same thing, but what if I told you they're actually completely different? Today, we're going to clear this up once and for all and get to the real science behind it.
Okay, you've all seen that classic footage, right? Astronauts just bouncing around on the moon, taking these huge, almost slow-motion leaps. It looks like a blast, but it really makes you wonder, how in the world are they doing that? What's the secret to their super-powered jumps? So, your first thought might be, well, it's gotta be something about them, right? Like maybe that long trip through space. Did it make them lighter? Or, to put it more scientifically, did they actually lose some of their mass on the way to the moon? The answer? It's a big, fat nope, not at all. And figuring out why that's the answer is really the key to this whole thing.
All right, to really get what's happening here, we need to break down two really important ideas. First up, let's talk about the constant in this whole equation, mass. And the easiest way to think about it is, it's all the stuff you're made of.
Yeah, that's really all it is. Mass is just the amount of matter in an object. It's the total quantity of stuff, atoms, molecules, you name it, that makes up you, me, a planet, a coffee mug, anything. It's the physical substance itself.
Now here's the absolute most important thing to remember about mass. It is constant. It never, ever changes no matter where you go. Your mass is exactly the same on Earth as it would be on Mars or just floating around in deep space. And we measure it in grams or kilograms, usually with a balance scale.
Think about a brick, for instance. It's made of the exact same amount of atoms and molecules, the same amount of stuff, whether it's sitting here on Earth or on the surface of Mars. Its mass is just a fundamental part of what it is, and that doesn't change.
Okay, so if mass is the thing that always stays the same, what's the part that changes? Well, that brings us to the other half of our puzzle, weight. And this is where gravity enters the picture.
See, weight isn't the stuff itself. Not at all. Weight is a force. It's the force of gravity pulling down on all that stuff, on all that mass. It's literally a measurement of the gravitational pull on an object.
And this is the crucial difference, right? Unlike mass, your weight can totally change depending on where you are because guess what? Gravity isn't the same everywhere. We measure weight in newtons, or more familiarly, pounds, and we use a spring scale, which is basically what your bathroom scale is.
It all comes down to a really simple rule, actually. The stronger the gravity, the more you weigh. So if you're on a bigger, more massive planet, its gravitational pull is going to be stronger, and you'll weigh a lot more.
All right, let's recap. We've got our two key players, mass, which is constant, and weight, which can change. Now, let's put it all together and finally solve the mystery of those high-jumping astronauts. So here it is, the big reveal. The moon is way, way smaller than the Earth, right? So its gravity is much weaker, only about 1/6 as strong. That means an astronaut on the moon has the exact same mass as they did on Earth, but the moon is pulling on them with way less force. So they weigh less. And that's it. That is why they can jump so ridiculously high. Let's just put this all in a nice, neat little chart. On one side, you've got mass. That's the amount of matter. It's the same everywhere, and you measure it in kilograms with a balance scale. On the other side, you've got weight. That's the force of gravity. It changes depending on where you are, and you measure it in pounds or newtons with a spring scale. See? Totally different things. To really let this sink in, let's imagine a quick trip around the solar system. Here on Earth, you have your normal weight. Hop over to the moon and bam, you weigh a whole lot less. But then, let's say you could somehow stand on the surface of the gas giant Jupiter. Its incredible gravity would make you weigh more than double what you do here. And through all of that, your mass, the amount of you, hasn't changed one bit. And hey, this also explains that whole weightless thing you see with astronauts floating around in space. When they're orbiting the Earth, they're basically in a constant state of free fall. They don't feel the force of gravity, which is why we say they're weightless. But, and this is the key, they absolutely still have all of their mass.
So if you need a really easy way to keep this straight in your head, just remember this. Mass starts with M, and so does matter. Mass is matter. And weight, well, weight is what gravity does to that matter. It's a pretty simple little trick to remember.
So there you have it. The next time you see that old footage of astronauts bouncing on the moon, or if someone cracks a joke about losing weight by going to space, you'll know exactly what's really going on. It's not about losing mass at all. It's all about gravity. And hey, it kind of makes you wonder, what other science words do we get mixed up every single day?